As you can see in this video, we're going to take a look at the intermediate value theorem. So if you're in my class, this is one of the first theorems that we are encountering. And when you're looking at a theorem is generally a conditional statement. There's an if part, which is the condition, and the then part is the conclusion. So if the if part, or the hypothesis of the statement, is not met, then the conclusion absolutely cannot apply. So one of the most important things about theorems is that you have to break down the words and you have to understand it. If you break the words down, you will understand the theorem. This is not hugely a calculus theorem. It's actually more of an algebraic theorem, and I call it a duh theorem because it just makes sense. So let me walk through this with you. The intermediate value theorem. So let's talk about intermediate. The word intermediate makes me think of in between. So that's how I'm going to break this down, and this is the good way to remember it, is let the words help you to remember it. So intermediate is in between. And then the word value is a number, and in particular, this particular theorem is talking about a y value. So we're going to be finding a y value that is in between other y values. All right, so let's take a look and let's break the theorem down and look at the conditions. If f, so first of all, I notice that this applies to a function because f is naming a function. If f is continuous on a closed interval from a to b. All right, so there's my condition. In order for this theorem to apply, I must have a function that is continuous on a closed interval. Let's go ahead and add that into our notes here. So I must have a function that is continuous on a closed interval. If I don't have a function that is continuous on a closed interval, then there's no reason for me to look at the conclusion of the theorem. So if I had a discontinuity somewhere in the closed interval, would not even consider it. All right, so that's the condition. All right, let's go back up to the top. And k, so here's k, is any number between f of a and f of b. Now, if it's a function value, f of a and f of b, f of a and f of b are certainly going to be y values. And I told you that this is a y value theorem. Therefore, when I go backwards, that means that k is also a y value. So if f is a continuous on a closed interval and I have a y value that is in between the y values generated by the endpoint. So the first endpoint is a, so that's a value of x. F of a is the y value generated by a. The other endpoint is b, so f of b is the y value generated by f of b. So over here on this graph, I'm going to randomly say, this is my value of a, and over here, this is my value of b. So let's say that f of a is somewhere down here, just so happens to be negative. There, it doesn't have to be negative. So there's f of a. And f of b is here. There's a y value. I don't know what it is, but it's a y value. So now k is any number between f of a and f of b. So k is a number between this y value and this y value. Now notice it says my function has to be continuous. So when I connect these 2 points, I can't lift my pencil, I can't make a vertical asymptote, I can't make a hole. So my graph might go up and back down and up and back down and up and go through B. Maybe the graph looks like that. So my graph is continuous on the closed interval. So from A to B, there are no discontinuities. So if k is a y value between f of a and f of b, then the conclusion is there is at least one number c, and c is an x value, on the closed interval between a and b such that f of c is equal to k. In other words, there had to be a value of x that generated that y value. So if we have a function that's continuous on a closed interval, and we said that k is between f of a and f of b, that would be another part of the condition. The promise is there is a value of x, and we're going to call it c, that f of c equals to k. In other words, the x value c generated the y value of k. That seems like a lot of words and a lot of, I don't know, gobbledygook, but let's look at an example, and I think it'll all make sense. So in the example, we have a continuous function, so that is a criteria that's met, and our continuous function happens to be named b of t. And this function indicates the number of students boarding the calculus bus at any time, where t is measured in seconds. If b of 0 is 0, so I'm just going to start forming a little graph here. The number of students at time 0 is 0, so I can plot that point. And then 2 hours later, 120 minutes, so there's my 120 minutes. There are 33 students on the bus, so this is 120, 33, and this is a value of 0 down here. It makes sense that if I'm going to connect these 2 points, whether it's linear, whether it's with a curve, I have a continuous function. Even if I stay linear, every value between 0 and between 0 and 33, we have to pass through them. In other words, you can't get to 33 without passing through 32 and 31 and 30 and 27.5, etc., 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 etc. So the question says, explain why there is, so it's going to happen, a time at which 21 students were boarding the bus. All right, so let me write that up for you. Let me get rid of all of this extra stuff that I have here. All right, so here's how I'm going to write up my intermediate value theorem. I'm going to start by declaring and claiming the conditions to be true. So I'm going to say, since b of t, that's my function name, is continuous on, and I have to declare my closed interval, 0 to 120. So I've met that condition. And f of 0, so I'm going to declare the first y value is 0, comma, f of 120 is equal to 33, so I've declared the second y value, and the number in question is 21. Since 21 is between 0 and 33, there must be a time on, and I'm going to reclaim my interval, 0 to 120, when at time t, when f of t is equal to 21. And I usually like to say by the intermediate value theorem, but you do not have to state the name of the theorem. You have to make sure the conditions are stated, and then you make the conclusion. So that's just a little short video on the intermediate value theorem. We will talk about that more in class and look at some examples.